At the end of part one, we left our project manager at a workshop using executives and getting their input for the 3-point estimates for the activity durations of the project. Now we're going to see why that's important and why PERT is so cool. What do you do with this? Well, remember that original project timeline or the network diagram that was put together based on just ballpark estimates by the project manager. Now the project network diagram is reconstructed, but this time using best case, most likely, and worst case estimates. You see this is BC, ML, and WC for best case, most likely, worst case. And these are combined using the beta distribution. It's a special type of weighted average used in PERT. Best case plus 4 times most likely plus worst case divided by 6. That gives the total duration of the project. So you've achieved something here. You know the critical path, and this entire schedule, the high-level schedule and the critical path, was derived using estimates from executives who are trying to get you speeded up. Okay, but there's also a benefit. Because each of these are created using a weighted average, the result is a sum of averages. And so that total is known as the project mean. What do you do with these? Okay, good question. You add all the estimates on the critical path. That is the overall average estimate known as the project mean. Because there's a project mean and all of these are created through 3-point estimates and weighted averages, you can also find the project standard deviation. And if you have a mean and a standard deviation, you can calculate the probability of achieving the estimated schedule. And you can show what duration gives a 95% probability of success. CPM cannot do this because it does not use probabilities. PERT can. So it gives you opportunity to include estimates of others, best case, worst case, most likely, combine them using averages, and then find the project mean, standard deviation, and you can start calculating probabilities. Okay, this takes advantage of the normal curve and how it works. You may have seen this image of marbles cascading through a grid. It forms a normal curve. Many things in nature fall this way. But there's an interesting property that the mean falls in the very center of the normal curve. Okay? This means if you're in the center of the normal curve, 50% of all, I guess in this case, marbles in the normal curve, are to anything to the left of the center, there's 50%. Anything to the right of the center is 50%. The mean splits the normal curve in half. Because we have found the project mean, what we have actually done is find the duration of the project that has a 50% probability of being achieved. That's an interesting number. So the number that arises out of 3-point estimates, in this case from executives who are pushing for project reduction in schedule, what they've come up with is something that only has a 50-50 chance of being achieved. And we can examine this by use probabilities by using areas under the curve. There's a 1, 2, 3 rule. Plus or minus 1 standard deviation, that's between the 1 and minus 1, is 68% of the area. Plus or minus 2 is 95% of the area. Plus or minus 3, that's 99% of the area. For example, if you tried to reduce an amount equal to 1 standard deviation from the project, you would need to take 50% and subtract 1/2 of 68%, which would be 34%. That's 1 standard deviation. So 50 minus 34 is about 15 or 16%. Here's the thing. If you can calculate the project mean, which is the middle of the normal curve, and the project standard deviation, you can decide, you can calculate how many units of time are equivalent to a single project standard deviation. So then if you're asked to reduce a project by so many units of time, You can convert that to how many standard deviations you're reducing, and then use that to indicate the probability of actually achieving that schedule.